Okay. Good morning, everybody. Let's stream. Today we're going to try to change it so that the objective function, so that the spirit term is not a regularization term added into the objective function, but rather it's a constraint. And that has some benefits, which we'll see in later streaming. Let's get started. We've come a long way. We've got a first version of spirit regularization up and running. It's probably debugged. And it seems to outperform just regular model-based reconstruction, which is, really wonderful. Today we're changing from this to this. That's our goal. Okay, so firstly, we're going to use the parameters lambda and sigma to decide which of these we're going to do. If lambda is greater than 0, or if lambda is non-empty, then we'll do this one. And if sigma is non-empty, then we'll do this one. So sorry, lambda and sigma will decide between doing this or doing this. If lambda is non-empty, then we'll do this. If sigma is non-empty, then we'll do this. But what if they're both non-empty? You can't do that. That's an error. That's what I put here. Then there's this question, what do we do if lambda is equal to 0? So we're passing in lambda, but lambda is equal to 0. Well, we shouldn't do this, right? We shouldn't do this code that we've created because square root of lambda is equal to 0, so we're doing all of these calculations just to yield 0. In C, the compiler might get rid of this. I'll bet you it will. But in MATLAB, it's an interpreted language. We will do these calculations. Totally forgot to let people know we're streaming. All of my 578 followers. So what to do about this fact that we're doing all these calculations just to yield 0? Well, if lambda is 0, if it's honestly 0, then we should just do regular model-based reconstruction. This form of regularization is sometimes called Tikhonov regularization. I think it's sometimes called ridge regression, though I'm not certain. Let's make sure what I just said is true. Yeah. I don't know what this problem is called. With Recon Spirit, we had this option to do multiple things, right? So if epsilon equals 0, then this. If epsilon's non-zero, then this. And we're going to do the same sort of thing like we did here, but we're going to do it here based on lambda and sigma. Okay. So I think apply W is going to be the same to everything. And we'll see what we need to pass in and what we don't. Okay, so if num L sigma is equal to 0 and lambda is equal to 0. Here we're just going to do model-based reconstruction. Else if num L sigma is equal to 0 and lambda is greater than 0. And here, Tikhonov. And that's going to be this function. Else I don't know what to do with these parameters. This, when we're done writing this code, this should never happen. Let's see. Let's see how close we get to that. Okay, so for this, we're going to need lambda for sure and apply W. And the S maps. And do checks. Do we have to do checks here? The parameter here is called do check adjoint. I see. So this code requires sensitivity maps. And then what we've been doing is, if you don't pass in the sensitivity maps, then it creates them. know if I like that. Instead, we're going to make the sensitivity maps required. We don't want to give people the false impression that Recon SPIRiT reg does not use sensitivity maps, especially since SPIRiT does not use sensitivity maps. Okay. Let's pass in a sample mask. Do we need more than that? Here, lambda is 1, sigma is going to be empty. What just happened? Let's try again. Here, lambda is 1, SPIRIT's going to be empty, so it should get to this line here. Let's see if that's what happens once we fix all the silly typos. Looks like we've got more silly typos. Okay. And sure enough, we get in here. Great. So we're going to be doing this Tikhonov regularization. Let's see what crashes. K data. We forgot to pass in K data. Let's do that, shall we? I'm moving the sample mask and the end samples into the code, into the function. We're going to have to do this for the function of this form as well. That's fine. We'll deal with that later. S image. The reason I'm passing these things into this code is because they're not used outside of these functions. Like they're not used to create W. Just makes sense to me. Why isn't ncoils being used? Like we had ncoils at some point. Ah, that is being used. Okay. To create W. Now in do checks, we can just do the check. That's strange. For W outside of this routine. So this will check the adjoint of W here. That way we won't have to replicate that check within this function and the function for the other form. We could just call this constrained least squares. Let's ask AI, what is the name of the optimization problem that is a constrained least squares problem where the constraint limits the result to a ball. Least squares minimization over a sphere. Okay. Can you provide the mathematical form for this problem? Or please provide. Trust region subproblem. This is an algorithm, not a form. Let's see if that's right. Trust region subproblem. Trust region subproblem. That seems more general than what we're doing. Yeah. Actually, it's more restrictive if that's the form, because here we have a ball. I like minimization over sphere. Okay. Else if num sigma is greater than, if sigma is greater than 0 and num lambda is equal to 0, then image is equal to MRI recon spirit reg min over sphere. And the difference will be, instead of lambda, we're going to have sigma here. We're just going to create a dummy variable, a dummy function, not implemented yet. Okay. Are there any typos? Yes. On line 183, what's the typo? Is inconsistent. Oh, right. Min over sphere. Is that the right name? Yep. Okay, now we've got no obvious typos. MATLAB is letting us set breakpoints. That's an indication that the code is right in some way, like no obvious typos, I guess. Does this run? S image. '97. Unrecognized function or variable S image. S image is here. I'm confused. Is it apply W? Yep, apply W needs S image. There you go. That's the image that we know and love. Okay. This is not the only condition under which we'll call MRI recon model-based. We might have sigma equal to 0 and numL lambda equal to 0. And I guess the one instance when we could supply both lambda and sigma is lambda equals 0 and sigma equals 0. Okay, in all three of those cases, we'll call model-based reconstruction. This will probably be the least used case because if we were going to do this, we might as well just call model-based reconstruction directly rather than calling recon SPIRiT reg. So I'm going to do this instead. This condition, or this condition, or this condition, then this. Otherwise, I don't know what to do with these parameters. I guess I should, the only way to get this is you can't, let's say, error. Oh. I guess I don't know what to do with these parameters is the right answer, huh? That just seems so colloquial. Sigma and lambda cannot both be set. Does that work? Let's move find W up because both of these functions, support functions, use find W. Or I guess. Also, if we're doing alphabetical order, then that comes first. Tikhonov element. So this would actually come first. If we were doing this in alphabetical order, which I've been resisting because we've been developing this first, then this. But actually, again, this will be the more common case. So now it's alphabetical and it saves an if statement, usually. Why not? There's one case where that is not, I said here both sigma and lambda cannot be set. But, and then, so these are the other cases. There's one other case, which I would like to be the most common case where numL sigma is equal to 0 and numL lambda is equal to 0. So we're going to handle this with apply W. rather with find W. Else why? Because we're going to let find W tell us what is a good value of sigma. So I'll say here, error not implemented yet. And it looks like we got a lot to do, don't we? Okay. Where is it? For this problem, we cannot use FISTA. FISTA solves problems of the form minimize g of x plus h of x, where g is differentiable and h has a simple proximal operator. This is the problem that we're working on. This is going to be g, and sure enough, it's differentiable. The issue's here. H is the indicator function for all the x that satisfy this constraint, and that does not have a simple proximal operator. If this matrix satisfied, let's call this matrix K, capital K. If this satisfied K transpose is equal to a scaled identity, then it would have a simple proximal operator, but it doesn't. We don't have it here. So we cannot solve this problem, I don't believe, with FISTA. So what do? Well, let's call this K. PDHG solves problems of this form, which is a more general form, where both G and H have simple proximal operators. This has a simple proximal operator. We'll let K equal to just that matrix. And so the question is, does the H that remains, the indicator function for this set without that K matrix in it, does that have a simple proximal operator? It does. It's just Euclidean projection. So we're going to use PDHG. We've got a few versions of PDHG in here. We're going to start out as PDHG, just regular with vanilla PDHG. Here I'm calling the matrix capital A instead of K. We have a lot of capital A's floating around, so we're going to call it K instead. Looks like I'm calling this F and G here. Okay, so I was slightly wrong earlier. This does not have a simple proximal operator. That without this matrix does. So let F equal 0. Then what's the prox of F? You just return the input. We're not using this variable because F is the 0 function. Certainly not using this parameter here, so we need to let it know that we're not going to do that. Okay, so now we've got, we could actually make this more simple. F is equal to at in. Prox F is equal to at in T. Oh, this should be 0, and this should be in. Okay. So now prox F is the handle to the anonymous function. Do we call that A or K? Guess we'll call it A. Let's see where that breaks. Let's call it K. Let's call it A. It's called A in PDHG. Okay, we'll call it A. So we're going to have to make all of these in order to get this thing to run. Might be unused? Why? It's right there. Maybe it's struggling with the fact that these things aren't set, so we'll worry about this error message later. There is a verbose, right? There is. Okay, now A is going to be a compound matrix. M, F, S on top, and W minus I, F, S on bottom. M is the sample mask, so let's find that. I usually don't put this stuff into the code. I can read these comments. Well, this is up above, so this is replicated. But also I could figure this out from the implementations of f and g, well, from the definitions of f and g. So maybe we'll leave this out later, these sort of comments. But for now, we'll leave them in. Okay, so apply MFS. So if nRn is less than 2, or string compare op, and let's make sure to not put a space right there, because that, dear friends, is a bug. Okay. We're going to multiply in, which for the adjoint, for the regular non-adjoint, for just the regular transformation, in is the image. So we're going to multiply that times the sensitivity maps. Let's apply S. Now we're going to take the f of t2. So it's going to be f of t shift 2, f of t2, I f of t shift 2. And now we're going to apply M. Now let's make this thing's adjoint. The adjoint of taking the values out of the sample mask is zero filling. That's why that thing is called zero fill. Now we take the adjoint of f and s in the reverse order. And so out is going to equal to, let's do the Fourier transform first. So f of t shift 2, f t2h, I f t shift 2, zero filled. I think here we do some S maps. We've gone through this before, so we could just look it up, but I think that's what we do. This doesn't have sensitivity maps. We can look down at Tikhonov. Here. Look at that. Some. Oh, the kanji. I'll totally mess that up. Here I'm meant to do this. So I'm going to do it like this. F H zero filled. So I'm going to break out S and F into two different things. S in is equal to ESX fun times, well, S maps in. Now, Fs in is equal to ft shift 2, ft2, I ft shift 2, S in. Out is equal to Fs in of sample mask equals 1. Why did I do that? Because now the adjoint is going to be more clear. We're going to do the adjoint, these things in the reverse order, one at a time. So here, this is MFSN, right? So the 0 filling is the adjoint of the M. I'll say MH. The adjoint of the mask in is this, is the 0 filled thing. Now we're going to take the adjoint of the two-dimensional fast Fourier transform on that. Okay, now out is equal to sum ESX fun. No. Conjugate of S maps times FHMHN. And we're going to sum in the third. Now, I knew there was a BSX fun somewhere that we didn't need. Here, S maps and FAHN are the same dimension, same size array. So we don't need BSX fun. We can replace it with just regular pointwise multiplication. $183. Oh. This was the issue with the verbose. Now everything's okay. And I'm going to run this with lambda equal to 1, which is what we have right now. We're just going to make sure, see, there's an issue. I was going to say we're going to make sure there are no issues, but it turns out there is an issue. What on earth is the issue of that? Operands to the logical and or operators must be convertible to logical scalars. Why isn't it? Sigma's empty. Oh. Huh. Okay. Let's fix that. We're going to try and get back to doing meaningful work in a minute. If num L sigma is equal to 0, sigma equals 0. If num L sigma lambda equals 0, lambda is equal to 0. And lambda comes before sigma because L comes before S in the alphabet. Okay, so we're there. Now let's go back to this. If sigma is greater than 0 and lambda is equal to 0, oh, but now this never happens. So this has to come after that. Now here, sigma can never be okay. For this little puzzle, I have to think just a little bit more. Let's see. What do I want to happen? If these are both empty, I want sigma to be set here. That's what this does. Okay. So if sigma if these are both, if at least one of these is non-empty, then sigma is not set. Okay. So then at this point, for the highlighted line of code, we can say for whichever one is empty, set it to 0. This find W should never set sigma to 0 unless some crazy circumstance where all the data values are 0 or something, just some pathological case like that. Okay, so I think this works now. So now we could just say, then we could just look at the values without wondering if they're empty here, because they're never going to be empty. So if sigma is greater than 0 and lambda is equal to 0 here, then we minimize over the sphere. If lambda is greater than 0 and sigma equals 0, then we do Tikhonov regularization. If they're both equal to 0, then we just do model-based reconstruction. Else, in this case, lambda is greater than 0 and sigma is greater than 0. We don't have a problem for that. And look at that, lambda is misspelled. Okay. I think that's resolved, and now we're back at the situation where we were going to do checks with the Tikhonov regularization. Why? Because we just changed something. Oh yeah, we just changed apply A. Let's see if apply A passes checks. It does not. Variable undefined. Undefined function or variable sk data. Sk data is equal to size k data. It's undefined because we moved that into the check for apply W, which is here. I would have thought we had moved it up here. Where's the check? There it is. Okay. Let's try again. A top passes, a bottom passes. Let's check A. A passes. Let's see if it gives us a reasonable looking image. Okay. That's the image we're used to, I think. So it looks like I was right. And we don't need this BSX fun. We can just do pointwise multiplication. BSX fun, when the arrays have the same dimensions, just does pointwise multiplication. So this is more clear, and I think it's more efficient. That brings us back here, and we have apply MFS. Here's that same pointwise multiplication. Let's do checks. If do checks equals true and Again, this would be much easier with Vim. I like Vim a lot. Okay, so let's see what breaks. Instead of setting lambda to 1, we're going to set sigma to 1. I don't claim this is going to make a good image. I just want to see what happens. We got in here. Surprising we got that far, honestly. The check passed. Okay. We now have MFS, which is the top of A. Function. Now we're going to create the bottom of A. Out equals apply W minus IFS. Now remember, don't put a space right there. That's a bug. This is interesting. S is in both here and here, so we're only going to apply that once. Like before, oops, I meant to do this here. What was I about to say? Oh, right, we're going to have A do the devectorization and vectorization. Do we need to do that with LSQR? I don't think we do. I think we could just leave it like this. N should be the right size. This implementation of PDHG and this family of functions that I've written in the dwarf lib don't require X to be a vector. So I think this should be fine. We don't have to make this a matrix, a vector. We don't have to convert from a vector to image and image to vector. Okay. So I think that we have to change this check because this is now apply MF. we get this far? Can we check if MF still works? Nope. Well, I mean, we could check, which is good. Still a bug? Check adjoint. Minimize over the sphere. That's strange. Oh. Okay. Where is that dot product being called? Here. Huh. Oh. Forgot to delete that line. And the check passes. Good. Help to solve a bug. Okay, so now here at this point, we've got SN coming in. What? Why aren't I paying attention? We have FS here and FS here like we did before. So this should just be apply M. This is the same code. The same code as in Tikhonov for A top. We can even call it A top. Okay. I like apply M better here. Instead of a bottom, we're going to call it that. Where does this? Okay, that gets used there. FH W minus IH, which is WH minus I in. Okay. Now here, I was wrong. I was a little wrong earlier when I said we wouldn't have to worry about vectorization and devectorization. A doesn't take in something of size image or size k data, or rather, A doesn't output something of size k data or size image. It outputs something of this concatenated size. So actually, we are going to output a vector from A. We won't need this one. Here, since we're not using LSQR, the in will actually just be a something of size image, so we won't need that. But we are going to output a vector. And so here we won't output a vector. For the adjoint of A, we'll just output something of size image, which out currently is. This is the devectorization of in is embedded in these two lines that are highlighted here. Okay? I think that's A. The issue is that we don't yet have apply W minus IF. And of course, this is no longer going to be apply W minus IF because F is already a part of A. We already have a apply W minus I, don't we? It's called A bottom here, but it's got lambda in it. Okay. Let's get rid of the lambdas. Might have been just as easy to rewrite that code, but whatever. Mm-hmm. Think the adjoint of A is going to pass? This is wrong. All right. Here we are. We need something of size equal to the number of samples. Shoot. No, we don't. We need something of size k data. So what was the problem? Out, not assigned. I see. All right. We faced this issue before. Okay, the adjoint of M passes, the sample mask. The adjoint of W minus I passes. No way. The adjoint of A passes. And we've got A implemented. We have F and A implemented. Now we need G. By the way, we only need F and G passed into PDHG if we're outputting the objective values, which we would only do for debugging purposes. PDHG does not need to calculate the objective values. Now, PDHG with line search probably does, but PDHG does not need to calculate the objective values. So we don't, if we weren't debugging and looking at the objective values, then we wouldn't pass in F. We wouldn't pass in F and G nor store the objective values, and PDHG is smart enough to know not to calculate those values and save the computation time. Okay, we need G now. So what is G? We don't need that comment because it's clear that F is equal to 0 from that line of code. Now we need G. So G of in1 is MFS times in, and M2 is this matrix times in. So I'm going to make it clear that G is operating on these two parts of the output. So G1 is this without the MFS. plus indicator of this without the matrix again. We're going to create two separate functions in one less than 2. I'm just checking to make sure that A outputs okay, we're going to have to worry about the size of N1 that G1 gets called with, which of course we will do later. E is equal to K data of sample mask equals 1. That's G1. Why did that happen? Oh, because I hit command down. G2 is equal to at into indicator function norm into the L2 norm. I guess to be more explicit, I could put that's the L2 norm. This is not the L2 norm squared. And the values that we want are between 0 and sigma. Okay? I think I know the prox of G2. Now PDHG takes in a value tau and sigma. Tau and sigma are typically called the two step sizes for PDHG. So it's slightly strange that we're calling this sigma here. You could call it epsilon, but epsilon is usually referred to as the numerical precision variable, which is why I called it sigma here. I guess we could call it gamma. Okay. So that avoids that naming conflict. See, does this comment help? I don't think it does, because we can see it from this function, right? Does this comment help? Well, we already know that PDHG solves problems of the form minimize f of x plus g of ax. That's what PDHG does. Okay. So I think I know the proximal operator of G2. The norm of N2 is that. If the norm of N2 is less than or equal to gamma, then out is equal to N2. Else, and out is equal to N divided by the norm of N2 times gamma. So this out here, out is a vector in the same direction as in, but it's been reduced in size to gamma. Now, yeah. That is what that does. I think that's the proximal operator of G2. Yeah, proximal operator of G2. Okay. Now we need the proximal operator of G1. And I do not remember. Luckily, I have a set of notes. We've been at this for an hour and a half already. Okay, so here's the proximal operator of the norm squared. And this is what it is. So if G1 were just the proximal operator of the norm squared, I'll bet you I have something for this in the dworklib. So I have a library called dworklib. It's just a directory filled with MATLAB functions. And then I set up this function called dworklib that I can use to search my library. So if you pass in a character array, it first tells you all the functions whose names match to that character array, and then it tells you all the functions where that character array was found within the function. I find this very helpful. I've got something called prox L2 squared. And sure enough, it's exactly what we want. Okay. out is equal to prox L2 squared in 1 T B, and then I think A is optional. Right, A is, oh, okay, so if you supply A, then for this general form, where A is arbitrary, we don't have a analytic expression for the proximal operator of there's a bug in this comment. We don't have a simple expression for the proximal operator of f, scaled f. But it's a convex optimization problem which you can solve with a conjugate gradient method. I think. I mean, I know it's a convex optimization problem, and I know that people solve it with the conjugate gradient method. But if A is overdetermined, I don't know what the conjugate gradient method does. The bug I was referring to is the proximal operator of TF, where F is, well, F doesn't have a T in it. Okay. So when we do not pass in an A, then this is what gets output. There's something called the separable sum rule for proximal operators. So G of n here we've got to split it up. Worklib also has a function for just the prox L2, not the L2 squared. There's also a bug here. Is that right? That doesn't seem right to me. Oh, okay. This is probably right. But G2 is not the proximal operator of L2 is the proximal operator of the indicator function of a ball. Which I do a lot. Maybe I should have a function called ball indicator. Prox ball indicator. A lot of variables. No, we're just going to leave it like this for now. Okay. Now, there's something called the proximal separable sum rule for proximal operators. For a function like this g, that are actually the sum of two different functions where the input is split into two parts. The proximal operator is the proximal operator of G1. Concatenating with the proximal operator of G2. We can make this an anonymous function. No, we can't, because got to split things up into N1 and N2. Now, we didn't actually need the proximal operator of G. We needed the proximal operator of G conjugate. This is always a little confusing to me. I'm going to call its scalar S. I'm a little confused. Let's go back to these notes. I think there's something called the Moreau decomposition. If you look at this, is explaining conjugate functions. This is the separable sum rule for conjugate functions. Here's the Moreau decomposition. Look, another sigma. We just need more Greek letters. So that's that sigma there. The reason I'm confused is because what if we don't have the proximal operator of f but tf, where t is a parameter? Then what? Ideally, I could do out is equal to prox conjugate prox g in S. But I'm confused because of that t. I'm going to think about that, and we're going to end the stream here today. We're making progress. We're on our way to having PDHG run to solve this problem where it's the constrained optimization problem, the minimization over a sphere, you might say. And then we also need to output gamma from find W. So there's a long way to go. And that's okay. Thank you, everyone, for stopping by.